one, action. So for the next part of our plate tectonic expressions lecture, we're going to move from divergent plate boundaries to convergent plate boundaries. Now, exactly what gets these started is still hotly debated. There are a few places in the world where we think they might be getting started as we look. Now, as with divergent plate boundaries, the expression of this type of relative motion is going to vary widely depending on whether you are looking at a continental, whether or not you have continental crust present or oceanic crust present. Now, this first one we're looking at is a picture of Mount Shasta, one of the highest peaks in California at the northernmost part of the state. You can see beautiful snow-capped mountain. And what you can see is diagram over here is kind of what's happening. But better than this diagram, 5, 4, 3, 2, 1, action! So if you remember on the map of magnetic anomalies for the Pacific Basin, you saw a lot of places where it looked like those magnetic anomalies were kind of disappearing as they ran into the continent. What's happened to those magnetic anomalies in actuality? Let's take a look. We're going to zoom into the northernmost part of California and also the coastline of Oregon and Washington. And if you look, sir, just even from a broad perspective, you see a couple things happening. You notice suddenly the coastline, the whole interior of the country near the coast, looks a little bit different in Oregon, Washington, and northernmost California than it does in the rest of California. You also see this very prominent ridge offshore that from this part of the region that you do not see over here. So we're going to zoom in and zoom in a little bit to where it looks all this stuff's happening. You also remember this is where we saw some of those magnetic anomalies disappearing. So that picture I showed you in the previous slide was one of beautiful Mount Shasta over here. And so let's see if we can zoom out a scale where we can actually see what's going on here. Perfect. So now we got a nice little scale to kind of give you a sense of what sort of spatial scale all of this stuff is taking. Five, 4, 3, 2, 1, action. So what we're looking at here is the first type of plate boundary. These ones are a little bit less, the order of them matters a little bit less than the divergent ones, though the third one, continent collisions, definitely tends to form after you've had at least one of the other two of these plate boundaries, probably both. So what you're looking at here is first you see an ocean, and of course underneath the ocean you have this oceanic crust, and this oceanic crust, oceanic lithosphere, is getting heavier over time and starting to die, and it's moving this way, whereas your continental crust is moving exactly where this, whereas your continental crust is moving this way. Moving this way. So what you're getting here, you have a nice big block of continental crust. You have your oceanic crust, and because they're coming together, your oceanic crust is denser. Your oceanic crust is going to start to dive underneath your continental crust. Crust as they're pushed together. Exactly what's driving this, that's a whole other story, but the denser ocean crust will sink beneath. Riding continental. And so what you have here is your oceanic crust. We'll put some lithosphere here in a moment. And so it's driving this densification. It's just that the stuff, over time, as the lithosphere cools, it gets thicker and thicker. You do have some lithosphere underneath here, underneath your continental crust, but a little bit less prominently. Let's also put a little bit of ocean water in here. I'm just going to put one other thing I'm going to put on this diagram to kind of explain what we have over here is just some sediments. So, whoops, wrong button. So what you're seeing in this diagram is you have oceanic crust coming together with continental crust. And continental crust. Crust coming together. Your oceanic lithosphere is sinking. Now, exactly what drives the sinking? There's a couple things driving the sinking. One is that the oceanic lithosphere is denser. But what happens is that as the oceanic lithosphere gets forced downwards, a second thing starts to happen to it. Your lithosphere will actually start to get denser. Lithosphere will actually get pressure and transitions crystallizes as and denser minerals will recrystallize. So what's ultimately driving a lot of this, believe it or not, is a chemical change of the oceanic lithosphere. And ultimately, once you start getting that recrystallization, that will, and in the case of this particular zone, you're getting, this will probably be taking place well outside of where we're looking, but that will continue to drive the subduction. Now, it's not just oceanic lithosphere that is sinking in this diagram. You're also getting, because you're under an ocean here, you're also dragging down quite a bit of water and sediments through cracks and stuff on your top of your oceanic crust. Now, most of this will just sort of ride along for a bit, but over time, as it gets deeper and deeper, it's eventually going to start to mix with the mantle, and you're going to get a slightly different type of melt here. You're going to get a water. The additional water is going to make a very different type of melt here. What we start getting is a water-driven melting of the mantle. And this water-driven melting the mantle is going to be more buoyant and going to start to rise. But it's not just water rising up here. And a couple things could happen. A lot of this stuff is going to, water-driven melting the mantle is going to crystallize at depth. Depth, forming continental crusts. But some of the stuff is going to make its way to the surface. And this is why you have, and not only is it magma making its way to the surface, in this magma, you also have substantial volumes of water. And so this water is going to be extremely hot. It's going to be under extreme pressure. And so when this water and magma finally do make its way to the surface, they are going to tend to explode. And so what you're going to get at the surface are these very tall, explosive volcanoes, like Mount Shasta, like Mount Rainier, or Mount St. Helens. you know, volcanism. And again, what we call this whole process, we call this process that's taking place here, we call it a subduction zone. Also, call this subduction zone volcanism. So the other thing you'll see in a subduction zone offshore is usually some kind of prominent trench. Now, the one you find off the coast of Oregon and Washington is not particularly prominent, but there are trenches that are much more dramatic. Trench. 5, 4, 3, 2, 1, action! So you see this not only, of course, in the coast of Oregon, Washington, but if you look around the Pacific Basin, you probably saw a lot of magnetic anomalies disappearing. You see a very dramatic trench in South America, like this one. Here, your subduction angle is going to be quite a bit steeper. You also see a whole chain of volcanoes running up and down the west coast of South America. Perhaps another spectacular one is the in Guatemala. You have this beautiful trench, and there was actually a pretty prominent volcanic eruption in Guatemala, the Fuego volcano, not that just a little over a year ago. And so, you notice, by the way, the steepness of the subduction angle can vary quite widely from one system to another. 5, 4, 3, 2, 1, action! So, for example, here in Central America, the Nazca Plate is diving down a lot more steeply. And so you're seeing, for example, this area of melt-driven magma reduction is a lot closer to the coast, and you have some very tall mountains like the peaks just behind Guatemala City, one of which blew up fairly recently. So now we're going to move on to volcanism. Now we're going to move on to the next type of 5, 4, 3, 2, 1, 0. Action! So now we're going to move over to the next type of convergent plate boundary, ocean-ocean. Now, when you get two pieces of oceanic crust coming together, you're going to get an island arc. So we're going to take you to one of my favorite places, and if you've ever looked for a deep place, we're going to go to the Northern Mariana Islands. What makes these islands particularly famous is, well, there's several things that make these famous, but one is that Guam is right here. Certainly has been in the news quite a bit lately. But more importantly, the deepest trench on the planet is just offshore of the Northern Mariana Islands. It's James Cameron and two other scientists have been there, supported in part by people, by engineers at a place I'm proud to say I used to work. Had nothing to do with that expedition, but I just like to say that I used to work there. So you definitely notice, first of all, the scale on this one's going to be a little bit zoomed out, but As you see this very deep trench, you see this chain of islands. And you have basically two pieces of oceanic crust coming together here. Five, four, three, two, one, action! So, just like in your ocean continent conversion, you have a couple important processes. You have subduction of oceanic crusts. Subduction taking place here. You have convergent plate motion here. And because you have water going down, and water even through the cracks of the crust, you're going to be getting some of this melt taking place. And this is generally going to be more melt, and you're going to be getting some volcano. This is why you get these chains of volcanic islands like this in the Western Pacific Basin. It's going to be, the volcanism is going to be a little bit lighter, and you're going to be getting and this little sliver sort of continent oceanic intermediate crust is not going to be as wide, and generally these islands don't really poke above the ocean too high unless there's other things that happen to sort of thicken this block of crust. But you are sort of generating the beginnings of oceanic crust, and it's thought that these represent some of the places where continental crust may have started. But the most prominent thing you see here are super deep trenches. Or these are more likely to be a fixture of ocean subduction than they are of they are of than they are going to be of ocean continents. And part of the reason is you don't actually get that much sediment coming off the continent in these settings. You're still getting quite a bit less. You're getting quite a bit less sediment flowing up the trench. In this case, you're also dealing with much older ocean floor. So in some place, much older ocean floor, so it's subducting a lot faster. 5, 4, 3, 2, 1, action! So now we're going to introduce another concept. So as you transition from one type of plate boundary to another, what eventually happens, one thing that'll happen is subduction zones don't just swallow up ocean floor. What they'll also do is they'll swallow up mid-ocean ridges. This happened in California about 30 million years ago, 30 to 10 million years ago, depending on where you are in the state. In fact, in the northernmost part of the state, you are still seeing it happen, and we expect that within a few 10 million years or so, the Gorda Ridge will be swallowed up. We're going to put another. We're going to create a kind of convergent 2.5 here, which is mid-ocean ridge has been swallowed, and now you're having continent being towed towards subduction. You start getting your continent being towed toward your subduction zone. Now, what's happening here is you are getting, what's eventually going to happen here is that this continent will not want to sink. Oh, so you still have volcanism here, but eventually, but this continental crust is going to be too light to subduct properly. So what's going to happen instead is these two pieces of continental crust are going to collide with each other. You're going to build up to a continent-continent collision. Let's take a look at a spot where that is happening presently. Five, four, three, two, one, action. The place we see that happening is here in South Asia. We have India, which has been being towed northward by a downgoing slab. And Eurasia, which is being brought southward by forces. But these two are basically ramming straight into each other. And so the boundary between these two is defined by the tallest mountain range in the world. Let's see what's happening here. Let's zoom in and see what's happening here. Remember my diagram of the continental material being towed in by a subduction zone. At this point, the entire ocean has been closed off. So we're going to look at Nepal and has been closed off. And all you have is continent on either side of your convergent plate boundary. You can kind of almost see in this with enough of vertical exaggeration. Now let's take a look at what's happening in the subsurface. Five, four, three, two, one, action. So looking at this now from a good side view, you still have your piece of continental crust marked by orange, being towed into another piece of continental crust that we'll do some more annotations on momentarily, being dragged down the subduction zone. But because this continental crust doesn't really want to go down, it's going to be dragged horizontally into this other piece of continental crust. And what you're going to see is, one, this continental crust is going to start to get mashed up and sort of behave in kind of a mushy fashion, where you're going to get little slivers of this continental crust are going to start to break off. And the net result of this is you're going to get super thick continental crust and very tall mountaintops. And so what you're going to see here is this kind of breaking apart and thrusting and thickening of your continental crust, giving you very tall mountain ranges. And so the way we'll label this is shortened and thickened continental crust shortens and thickens. Thickens. You notice right here on the bottom lower left, we still have some piece of oceanic lithosphere that's dragging this whole bugger down. But yeah, dragging this whole bugger down is still powering this process. But for now, but what's happening is the primary motion of the continental crust is going to be horizontal. So you're going to get this shortening and thickening, giving you a super tall mountain range. Range like the Himalayas, such as the Himalaya. And so the Himalaya represents some of the thickest continental crust, or any type of crust, on the planet. Now, you might notice there's something missing here. Because you don't have an ocean here anymore, you do have some oceanic sediments. The summit of Everest actually has a little bit of a seafloor limestone, but because you don't have any mechanism to bring water down the mantle, and you also are lacking any mechanism to decompress the mantle. If anything, the mantle's under more pressure. You do not have volcanism. So, we're going to call this plate boundary convergent plate boundary number 3, continent-continent collision. And this just about wraps up everything we're going to be doing with convergent plate boundaries. On the next sequence, you'll be looking at transform plate boundaries.